Okay, so hello everyone. Welcome to this session of 15-minute Hikka. So we have been running a series on artificial intelligence since the last four lectures, and this will be the fourth one, and this will be on natural language processing. And we are really delighted and grateful that Professor Jugal Kalita of University of Colorado at Colorado Springs has joined us to give a talk on natural language processing, introduction to the state of the art. I'd like to give a brief introduction about Dr. Kalita. So he received his BTech degree from IIT Kharagpur in 1982, then an MSc degree from University of Saskatchewan in Canada in 1984, and then MSc and PhD degrees from University of Pennsylvania in US in 1998. He teaches a variety of classes at UCCS in computer science and related fields. He is also an administrator of National Service Foundation, Science Foundation's grant for undergraduates in computer science, mathematics, and engineering, and has been on the program committee for several conferences, including CKDD, which is a very well-known conference in machine learning and data mining. He is also the founder of the Bioinformatics and Biotechnology Symposium, and his research interests are in artificial intelligence, natural language processing, bioinformatics, and information retrieval. And he recently authored a book called Machine Learning Theory and Practice for as a machine learning textbook, which just came out. So we're really delighted and happy that Dr. Kalita agreed to give us this talk. He's a really well-known in this field of natural language processing. So without further ado, so I'll ask Dr. Kalita to start his talk. Thank you.
Dhanyabad, Iraq. Namaskar. মোৰ নাম Jugal Kalita. মই আছো কলোৰাডোত আৰু অকমান মই দেখুৱাম ভিডিঅ'ত মানে বাহিৰলৈ কেমেৰাত দেখুৱাম বিৰাট ঠাণ্ডা বাহিৰত দেখিছেন নে ক'ব নোৱাৰো বৰফৰে ভৰ্তি হৈ আছে ইয়াত এতিয়াও আৰু প্ৰেজেন্টেশ্যনটো হ'ল মই শ্বেয়াৰ কৰিম এতিয়া Zoom মই ইমান ব্যৱহাৰ নকৰো গতিকে মাজে মাজে খেলিমেলি হ'ব পাৰে
ঠিকে আছে আহিছে দাদা
দেখিছে Hello
ঠিক আছে
I'm a professor in the Department of Computer Science at the University of Colorado Springs. I've been working in natural language processing for the past, I would say, I don't know, starting 1980, so for the past 42 years. And what I'm going to do today is give a very high-level overview of what natural language processing is, and then go into one topic and show what the state of the art is. All right, so people have heard about this thing called ChatGPT that came online maybe a month or two ago. So I went onto ChatGPT a couple of days ago, 2 days ago, that's on Thursday, and gave it a command. Write a paragraph on Assam, that's JK, that's me. Then starts writing fluent English. Assam is a state located in the northeastern region of India. It is known for its rich cultural heritage, diverse wildlife, and tea production. The state is surrounded by lush green hills and forests, making it popular tourist destination for nature lovers. And it goes on and on, the whole paragraph. Then what I did was to write another paragraph on Assam. It continues. Assam is a diverse state, both culturally and linguistically. It is inhabited by numerous ethnic and tribal groups, each with their own unique customs, languages, and traditions, and so on and so forth. So that is the state of the art in machine learning-based natural language processing. So let's continue with this. So I say, write a third paragraph on Assam. So I'm trying to get the machine or ChatGPT, the program, to write an essay for me, and it continues. Assam is an important state in the northeast region of India and has rich historical background. So there is some repetition, but it also goes in the second sentence. It has been ruled by various dynasties and empires throughout history, including the Ahom Kingdom, which ruled for more than 600 years and had a significant impact on the state's culture and traditions. So all good. Then I said, okay, let me try to do it in Assamese. Ahomiyat likhokson. My machine to kolu, Ahomar bihe likhok. Etia machine to a bulgur alarm korila. Ahomia aru Bengali miholai die. Ahom Bharater Uttar Purbat Pradesher একটি রাজ্যে এনাকে লিখিব আরম্ভ কৰিলে ইয়াত দেখিলে মোৰ কাৰ্সৰটো দেখিছেনে বাৰু
দেখিছে yes
okay অসমৰ এটো অসমৰ দেখিলে অসমীয়াৰ চাৰাগ্ৰহী হয় এটো কি মই বুজি পোৱা নাই কি লিখিলে আৰু বাক্যবিলাকত ভুল আছে ফ্যাকচুয়াল ভুল আছে কনস্ট্ৰাকচনৰ ভুল আছে বঙালীত হলেও মই কলো অসমীয়াত লিখক আকৌ এবাৰ ভুল কৰিছে কাৰণে অসম একটি মহান ৰাজ্য এনে ধৰণে কোনো কথা নকয় তাৰ ইতিহাস এবং সংস্কৃতি এক গুৰুত্বপূৰ্ণ হবে a sentence or বাক্যবিলাকৰ the syntax is starting to go wrong and spelling অসম ইন্দ্ৰিয়া স্বাধীনতা আন্দোলনৰ প্ৰভাৱী হৈছে ইন্দ্ৰিয়া ভাবিছে to ক'ব বিচাৰিছিলে ইন্ডিয়া গতিকে ভুল কৰিবলৈ আৰম্ভ কৰিলে ইয়াৰ পিছত মই আকৌ কলো এইডাল গুচাই দিব লাগিছিল এইডাল ঠিক আছে অসমীয়াত লিখিব লাগে আকৌ অসমৰ বিষয়ে লিখক তিনিবাৰ মই চেষ্টা কৰি চাম আৰু পাৰে নে নোৱাৰে অসম একটি উত্তৰ পূৰ্বী ভাৰতীয় ৰাজ্য যেখন তাৰ স্বাধীন জনগোষ্ঠী ইন্দ্ৰিয়া হৈছে কোনে জানে কি কৈছে এইটো the English was pretty good. The English essays are pretty good, but as soon as I said writing Assamese, Ahomiyat likhok, it started making mistakes. But anyway, at least in English, it's doing very well. And then I wanted to bring up a paper one of my students wrote. This was in 2020, 2019, maybe 2 or 3 years ago. And the title is Introducing Aspects of Creativity in Automatic Poetry Generation. A GPT-2, the ChatGPT is based on GPT-3. This is a paper based on what GPT-2 can do. So in this paper, we asked or trained GPT-2, the previous version of GPT, to write poems. So this gives an architecture of how GPT-2 could have been, we trained GPT-2, it's already so-called pre-trained. It knows language fairly well, GPT-2. It's a neural network architecture. What it is, it's not important, but it's a machine learning program that has been trained on a huge amount of text, of billions of web pages and other pieces of text. Then we train it again. So it's as if someone who knows English well, in general, we train it again on texts obtained from the Gutenberg corpus, which is a free corpus of old books. But we went there and found books that talked about trust, books that were about sadness, books that were about anger. Then we started, once we trained it, we wanted it to generate poems. So it could generate poems. The paper actually, as you can see, our program generated poems and poems of different kinds, For example, this is a poem that shows some kind of joy. Heard I is song of joy, it's song of happy sound, so on and so forth. Then we said, write a poem that talks about sadness. A long trail of falling mist had made its way here and now. Early it seemed as if to drown. So it starts using words that are sad. So that was done about 3 years ago. Then so we looked at GPT-2 and GPT-3. GPT-2 have been there for the past 4 years or so. GPT-3 is fairly new, and ChatGPT is based on GPT-3. ChatGPT works well. That's the state of the art. That's how it is right now. ChatGPT works well in English and possibly a bunch of languages, but doesn't work well in Assam. Then I wanted to look at another state-of-the-art program, so I went to Google Translate. So I took the paragraph that GPT or ChatGPT had generated on Assam and wanted it to translate into Assamese. So Assam is a state located in the northeastern region of India. Very nice translation. It is known for its rich cultural heritage, diverse wildlife and tea production, Sohoki সাংস্কৃতিক ঐতিহ্য বৈচিত্ৰ্যময় বন্যপ্ৰাণী চাহ উৎপাদনৰ বাবে জনাজাত অকমান এইখিনি আৰু দিব লাগিছিলে তাৰপিছত প্ৰথমতে এইটো ড্ৰামাটিক আৰম্ভ কৰিছিলে চহকী সাংস্কৃতিক ঐতিহ্য কিন্তু অলপ খেলিমেলি হৈছে the state is surrounded by lush green hills and forests সেউজীয়া ভুল কৰিছে দুবাৰ বনাই দিলে সেউজীয়া দুবাৰ লিখি দিলে পাহাৰ আৰু অৰণ্যৰে আগুৰি থকা ৰাজ্যখন প্ৰকৃতি প্ৰেমীৰ বাবে জনপ্ৰিয় পৰ্যটনস্থলী Do you know, this is actually very good. One can take the English paragraph, put it into Google Translate, get a translation. It's not 100% correct, possibly, or may not be 100% perfect, but one can go ahead and edit it and make it look nice. So let's look at another state-of-the-art program. So this is Bing, Microsoft Bing. Microsoft Bing also actually is pretty good these days. The translation program is pretty good. So I took the same paragraph and asked it to translate. And let's see, let's look at this third sentence. The state is surrounded by lush green hills and forests, making it a popular tourist destination for nature lovers. এইটো বাক্যটো অসমীয়াত হ'ল ৰাজ্যখন সেউজীয়া পাহাৰ আৰু অৰণ্যৰে আগুৰি আছে তাৰ ফলত ই প্ৰকৃতি প্ৰেমী বা সকলৰ বাবে এক জনপ্ৰিয় পৰ্যটনস্থল হৈ পৰিছে Good translation. গতিকে মই কি কৰিলো এতিয়া এইটো হ'ল ইংলিশটো এইটো হ'ল Google Translate এইটো হ'ল Bing Translate আৰু মই যি দেখিছো the translation quality is actually pretty good so that's the state of the art Google Translate, Bing Translate, they know Assamese fairly well. They can translate from English to Assamese fairly well. Maybe, as I said, not 100% perfect, but this is like how most people write. If someone is a student, someone is not a literary person, it's how they might be able to write. They may be writing. So I gave you 2 examples of machine learning-based natural language processing or natural language processing. One example is give the program some instruction, write a paragraph on Assam, or where is Assam located? Ask a question. That ChatGPT will give us a paragraph or a response. That's like Google in some ways, but much more generalized version of Google search engine. Google search engine, you put a search phrase or a search sentence or word and gives us results. Maybe for the first result, it gives us a summary of what's there in the page, but for the others, it just gives the URLs and it picks up some portions of the web page and highlights it, whereas ChatGPT is going to be much more human-like. Given a question, given an instruction, given a command, it's going to respond like a human being. And Google Translate or Bing Translate, they can translate among 100 plus languages of the world. Assamese was added to Bing Translate maybe 2 years ago. Google added it only last year. Okay, so that's the state of the art. Does anyone have any questions? Then I'm going to go into some technical details at a high level, not very deep. If someone has a question, I can answer at this point in time.
There are some questions from the chat.
Chat.
Yeah,
Can you-
Jugal, Arati asked, Jugal, did you try asking a paragraph on, say, Maharashtra or something
No,
else? to
I did
compare?
not try it because I wanted to make this presentation geared towards most of the attendees here who are from Assam. So I didn't try that, no.
Okay. Jubin asked, does ChatGPT store conversations?
Quite likely everyone is storing everything. So quite likely it's storing the conversation. If you ask to search in Google, it'll store your search. If you do go to Google Maps, it'll store that unless you go and tell it not to do it. Quite likely ChatGPT is doing it also. Everyone is saving things possibly to improve the performance. I put in some comments there in ChatGPT in Assamese when it was writing in Bengali or bad syntax, or it was making mistakes. But yeah, quite likely everyone is saving everything you do, either for commercial purposes or to make the product better later. All right, so I'm going to move on. So when you talk about natural language processing, there are 4 kinds of processing or 4 kinds of things that could happen in natural language processing. And they are, like you see here. Can you see the whole screen, or you see all these pictures there? I would like to.
Yeah, we can see the whole screen.
Dara, can we request you to kindly disable annotation? I think you can disable annotation because someone is annotating something on the screen.
Okay, where do I?
You can go to the top. So you will see a small bar. There you can find annotation on your side. Can you see it?
No, I don't see it. Oh, annotate.
Yeah, then you can
Stop
disable
share.
annotation.
Mouse, clear, save. I don't see disable, really.
Yeah, thank you. Thank you. And maybe request everyone on the Zoom chat to kindly stay away from doing something like that. Thank you.
Okay.
Sorry, sir. Please go ahead.
All right. So what's going on here, if you see, when you perform natural language processing, the tasks can be of various types. One kind of tasks are so-called one-to-one. So for example, given a word in one language, it could give you the word in another language. For example, if I say Warhahali, it could give me a school. Or it could be one to many, one to one. One is bottom, one is top. Or it could be one to many. So if I have written a program that generates essays, I could just type in the word Assam, and it's one word. Then it's going to do some processing, but it's going to generate a whole bunch of words. So that's one to many. Or it could be many to one. So I could write a whole lot of text and ask, what's the sentiment expressed? Is it positive sentiment or negative sentiment? So given a lot of words, a sequence of words, it's going to give us one response. Or it could be many to many. For example, given a sentence in English, or given a whole paragraph in English, it translates to a whole paragraph in English, or in Assamese. So many words in English are converted, are processed, and transformed to many words in Assamese. So these are the 4 kinds of natural language tasks at an overall basis people can identify. And when we talk about translation, talk about the way ChatGPT works, those 2 programs are many to many kind of programs. So many to many sequence of words in one language are processed and then transformed to sequence of words in another language, or sequence of words, doesn't matter, they don't have to be different languages. A sequence of words are transformed into another sequence of words, and that's called a sequence-to-sequence task. So what I'm going to do in this presentation, in the next part of the presentation, I'm going to focus on, there are too many different things people can do in natural language processing, but I'm going to look at only one of these tasks and look at the state of the art, that's translation of natural language. So given a document in one language, language 1 is source language, would like to see how it can be transformed into a sequence of words in another language. Okay, and once again, this is sequence-to-sequence task. And we'll focus on the translation task in this presentation because it's supposed to be 15-minute hiccup, under a minute hiccup, so it's going to be about an hour or so. All right, so let's look at the idea of translation. This is from Juravsky and Martin's book on natural language processing. And so what we have here is a sentence in Chinese translated to a sentence in English. Again, a second sentence in Chinese translated to a sentence in English, and so on and so forth. And people who are attending and people who speak another language, of native language, or just speak 2 or 3 languages are used to translation, but let's look at some issues in translation. Okay, so this is the Chinese, but it's written out like it's in English. So the words, the Chinese words are not given here because they'll not be able to follow, but clearly we see fall down tears. We have 3 words here, fall down tears, but in English it becomes cry. So 3 words in Chinese, they become 1 word. Okay, then there are words like it, she, almost. There is no Chinese counterpart for the word almost. Almost without noticing it, she had begun to cry. So these 3 or 4 words, 1, 2, 3, or 4, 5 words, there is no counterpart in Chinese. Then let's go up to the first sentence here. Chinese, like Assamese, it looks like, as you can see, what is going on here. The name of the person comes up first, and when you write it in English, somehow the word Dayu, that's someone's name, it comes out quite in the middle of the sentence. So what has happened is the word Dayu, which occurred first in Chinese, moves to the middle of the sentence here. Then Dayu here is a direct subject, whereas in English, when someone performed a translation, this is professional translation, it became Dayu, it became possessive. Then think is a verb in Chinese, that was a Chinese verb, but it became noun in English. So there are lots of problems in translation. Translation is not straightforward. Quite often, words and components of a sentence, they move to different places from one language to another. Whenever we have this crosses here, that means words have moved around. They're not in the same sequence. words in one language are not sometimes translated in the other language. So we have no word here and it becomes the. Sometimes what happens is a whole bunch of words need to be inserted in another language, so it becomes actually understandable translation. So let's look at some of the problems here. English and Chinese translations are very different structurally and lexically. Sometimes several sentences in one language, they become one sentence in another language. The word order is very different. And we can see that if we compare Assamese and English, if I just say, I like movies. So I have I, which is the subject, like is the verb, movies is the object. So it's a subject, verb, object language. English is an SVO language. Subject comes first in general, then the verb comes, then the object comes. But if we talk about Assamese, say the same translation sentence would be moi cinema bhalpa, moi kotha sabi bhalpa. Moi is the subject, kotha sabi or cinema is the object, then we have the verb in whatever form. So it's a SOV language. Subject comes first, object next, then the verb at the end. So words move around. Then if we talk about English and French, in English, if we have a noun phrase, let's see, the adjective, if we have an adjective, the adjective comes before the noun. In French, the adjective will come after the noun. If we want, take another example, if we say, if we have a little phrase, the boy. The is the article, it occurs before the noun, the boy. But if we write the same phrase, translate into Assamese, it'll become Laura too. So in English, the article is a separate word, it comes before the noun. In Assamese, Laura is the noun, tu is the article, but it occurs after the noun and it gets conjoined into one single word. So there are lots of problems. So another one we can see here, quite often, or in English or in most European languages now, Western European, the names of people, at least the first names, Peter, John, they are not words in the language. They were words in some language maybe 2,000 years ago, but they became now fixed, and those are the names. But in Assamese, or in a lot of languages, if we take my name, Jugal, take a Hirag's name, Hirag, those are actually dictionary words. Paban Sahoria, that Paban is a dictionary word, means air. Okay. So quite often, as you can see, in many languages, names of people are actual dictionary words, and that makes it very difficult to translate. So there are lots of problems, lots of difficulties in translation, and these are just a few examples. So how has translation been performed? There are at least 3 ways of performing translation. People started, or computer scientists started performing or writing programs for translation from the 1940s when computers became available. And from 1940s to 1980s, it was the time of so-called classical machine translation, 1980s to early mid-2010s. So till about 10 years ago, it was statistical machine translation. And now, starting from the mid-2010s, about 2015, 2016, we have what's called the age of neural machine translation. So let's look at these 3 approaches: classical machine translation, statistical machine translation, and neural machine translation. There are different approaches to classical machine translation. One approach is, given a sentence, Mary didn't slap the green witch. So this is an English sentence. We want to translate it into Spanish. What has to happen is, first we need to go over each one of the words and do what's called morphological processing. That means if we have a complex word like didn't, so it actually is due in the past tense. So we need to know the tenses of the words, and didn't became due past and not. Then we need to know the genders, possibly. We may need to know the number, plural or singular, but we'll first do morphological processing, then translate each word. Mary becomes Maria. Not becomes nose, which becomes green becomes verdi, which becomes rua. So each word needs to be translated one by one by one. But when we translate it one by one, word by word to another language, the order becomes messed up. So we have to go ahead and change the wording of the words. So it's okay in the second language. And then we need to do the proper spelling. Morphology means proper spelling, put words together, and so on and so forth. And that's the way translation has to be performed. So first, given a sentence in English, we translate word by word. First we do a simple processing of the word, spelling processing, then translate word by word, change the order, and then write out the proper spelling. And that's how machine translation was performed, but this essentially means it was a very complicated process. Another approach for classical machine translation was that, given a sentence in one language, if we want to translate it into another language, first what we do is take the sentence, he adores listening to music, in the first language, and diagram it. That means parse it, obtain the various components, obtain how they're put together. Then, because we need to translate it to another language, what we need to do is reorder. So we need to go into this tree structure, move parts around, and once you move parts around to conform to the second language, then you can start translating. So again, it's similar to what we did before. It's a more algorithmic part of way to look at it. Okay, and so if we look at the first two approaches for classical machine translation, suppose we have to translate from one language to another. What do we have to do? For each pair of languages, we had to write rules. Which word, so we had to have dictionaries, bilingual dictionaries. So which word translates to what are the then we have to have rules. What are the morphological rules in the first language, spelling related rules? What are the spelling related rules in the second language? Then we also had to know how things needed to be reordered. So if we have like Google Translate now or Bing Translate, suppose we have 130 languages. Anyone can be the first language, anyone could be the second language. So we have 100 times 100. So we have 10,000 pairs of languages that are possible. Then for each one of these 10,000 pairs, one had to write up the rules. How to take the tree structure in one language and translate or transform it to the tree structure in another language. It became very complicated. It's not scalable. And so classical machine translation is not scalable. So near modern approach to statistical machine translation, which people used from say the 1990s or mid 1980s to 2010 or so, it said it's too difficult if we have to write rules for each pair of languages, we cannot scale up. It's not possible. So let's see if we can do something else. If we can, without having to write grammatical rules for a language or for each language, then without having to write translational rules or for each pair of languages, what can we do? So let's look. So to be able to do statistical machine translation, SMT, as you can see, or to be able to do machine learning based translation, we need so-called parallel texts. So if we look at Canada, Canada has two official languages, French and English. In the Canadian Parliament, every document, as soon as it's produced in one language, it's translated to the other, and it's made available quite often on the web now. If we go to the European Union, there are 24 languages. They're all equal in stature. Anything that's written in one language, spoken in one language, is right away translated to 24 different languages. The UN has 6 official languages. All documents are produced in parallel in all those 6 languages. So we need so-called parallel resources to perform statistical machine translation or machine learning based machine translation. And most of these come from government documents. But let's now assume we have, hello, can you stop writing? Someone is writing on the screen, so it's all showing up, the scribbles. And I don't know how to stop it, but please don't scribble. So it makes it difficult for others to follow. Anyway, so this is an example from 1997 from a paper by Kevin Knight. And let's look. What we have here are 2 languages, made up languages. This is a set of sentences in one language. 1A is a sentence in one language called Centauri. There's no language called Centauri. It's made up, just to give an example. The second sentence is a language called Arcturon. This is also a made up language. But the point here is that what we have here is a pair of sentences, one in language 1, the other in language 2. We have another pair of sentences, one in language 1, the other in language 2. And so on and so forth. And quite likely in current machine learning based translation or statistical machine translation from about 10 years ago, we'll need millions of pairs of sentences like this. Okay, given a bilingual corpus, given this is a bilingual corpus, statistical machine translation is going to try to translate without any knowledge of the 2 languages. Statistical machine translation doesn't know the languages, doesn't know the grammar, doesn't know the words well, but it's going to try to learn to translate automatically from a data set like this data set being a bilingual data set, bilingual corpus or body, where we have sentences in one language followed by the same sentences in the other languages translated officially. So let's try. Okay, so what we are asked to do is, given this bilingual corpus, then we're given a sentence in the first language and asked to translate to the second language without knowing anything about the 2 languages, nothing except for this bilingual corpus. So the first word that occurs in this sentence to be translated is some made-up word Farag. So we go over each one of our sentence pairs and to see, the word Farag occurs here in language 1, and word Farag occurs there in a sentence, another sentence in language 1. But whenever Farag occurs in the second language, we have the word Jat occur, we have the word Jat occur. So statistical machine translation is going to do some computation in numbers, saying quite likely, maybe anytime we see the word Farak in the first language, it translates to Jat in the second language. So it kind of hypothesizes Farak translates to Jat because anytime in a sentence in one language, one Farak occurs, Jat occurs. Okay, but then what about this word, Karak? It goes through 1A, 2A, 3A, 4A. It finds Karak in only one sentence in language one. And now, because it finds it only once, it doesn't see a pattern. So it's looking for patterns. It doesn't know how to translate. Okay, then it looks at the third work, Hihak, in the first language. So it needs to know how to translate it. Okay, so it looks at 1A, 2A, 3, it sees the word Hihak and goes on and on. In 11A, it sees the word Hihak. In 12A, it sees the word Hihak. And then what happens is, let's see. So anytime the word Hihak occurs, the word Arat occurs. Arat occurs in the second language. It's going to hypothesize based on statistical computation that Hihak translates to Arat. So what it's trying to do is learn patterns. Statistical machine translation is going to look at sentences in language one, like the A sentences, sentences in language to the B sentences, and look for statistical patterns of co-occurrence, and is going to try to learn how to perform translation. Anyway, so it'll continue like that. There are different ways to do it. People came up with very complex algorithms, how to look for patterns. But the essential idea in statistical machine translation was that the program did not know the languages. The program did not know words in the language. The program did not know syntax. The program doesn't know meaning, nothing at all. It's just looking for patterns, trying to find translation. So that was the first set of examples. They were made up languages, but here we see a real Spanish-English bilingual corpus. So we have a sentence in Spanish or English and the corresponding Spanish. English, Spanish, English, Spanish, English, Spanish. We'll have to have possibly millions of pairs like that. And once you have millions of pairs, it can learn patterns and can perform translation. So that's statistical machine translation. I can stop here for a minute and ask if someone has questions.
Yeah, there are some questions from the chat. So Arati asked GPT-1 regarding GPT-1 and GPT-2. DDR University bought the software.
No, GPT-1 and GPT-2, they were available for free. Now GPT-3 has become difficult. They're asking for money, but this was like 5, 6, 7 years ago. So at that time, you could just use them for free.
Okay.
But now GPT-3, I think they're starting a subscription process. You have to pay $20 a month because someone invested money, definitely, possibly hundreds of millions of dollars. Initially, they were doing it for nonprofit, but now they see potential to make money and they're selling service.
Yeah, so Jubin Rava from Dudhnoi College asked, why should artificial intelligence be defined according to machine deception of people?
Machine what?
Machine deception of people. Or maybe he meant like a human replacement or something, like an agent that can...
Artificial intelligence tries to mimic or write programs or develop algorithms for tasks that human beings do well and machines have not been able to do well traditionally. And so for a long time, it was because of military needs. The first AI programs, especially in NLP, they occurred because of the Cold War between Russia or USSR and the United States. The USSR and United States, they were both trying to be the supreme power in the world. So any document that was written in Russian, the United States wanted to get it translated to English right away. So some of the first works in artificial intelligence started in translation because of defense reasons. I can see valid reasons. India and China, they're not friends. So any document written in Chinese, maybe India wants, by the government, if the government of India can get its hands on Chinese government documents, it wants it translated to, say, English right away. So that's defense related. Another one could be, say, now I'm here, and Zubin Rava Dudnoy Boyase, but maybe you are doing a search for something, and the document you need, you're trying to write an essay, write an article, or whatever it is, doing some research. Maybe the article that you are interested in written in Japanese, and you can get it translated right away. So it has become very valuable. Anything in the world is available to almost anyone else in the world. So those are some positive things in AI. But at the same time, anything good can be used for bad. So it's possible that someone could look at samples of your writing, then train a machine learning program to mimic, then write a letter to someone else, something saying very bad things to someone else in your in the style you write. So there are positives and negatives. Most AI scientists, they worked on the techniques, and I know it's not really the best answer possible. Most people don't really care about how it's used. They're interested in the science of it, the engineering of it. But once again, science and engineering, they don't happen for free. Governments, companies fund all the programs, all the projects people work, and so governments and companies are going to use the technology for whatever they want to. So quite likely what has to happen is, if we want to do this well, international organizations, governments, companies, they have to come up with their own rules of ethics regarding how AI is going to be used.
Yeah, so, Zubin has one more question. Has any new model been able to beat GPT-3 when it comes to machine translation?
GPT-3 is only, what, about a year old. So GPT-3 doesn't have to, it's not, I don't know the real answer to that question, but GPT-3 is available to the world. So anyone can go and get something translated or get something written up. But research is performed, a lot of the research is performed, and GPT-3 must have taken hundreds of millions of dollars to actually train and produce the model that they can produce and make it available to the world. But if I'm performing research on similar topics, I'm one single individual with maybe 2 or 3 or 4 students. I cannot compete with GPT-3. But so what happens is, when people do research in universities, we look at very small aspects of things, and so trying to make it scale up. So quite likely I may be working on how to translate, for example, noun phrases well. Instead of trying to do 103 languages to 103 languages, I'm looking at only 2 languages. So GPT-3, I would not claim it's the best in the world, but it's something that's have been scaled up and have been made available to the world. And it's kind of like the, it's very good, but again, GPT-3 or ChatGPT, they're known for being available to the entire world. It's like Google search engine or Google Translate, or there are programs that are likely to be better than Google search engine, but other people don't have the money to make it available to the entire world. So anyone from anywhere in the world, they type something in and they get a response within seconds. So that's how we need to see something like GPT-3 or ChatGPT.
Yeah,
okay.
Thank you for your answer.
I'm
So
gonna
those are the
move on.
questions currently we have. Yeah.
All right, so how does statistical machine translation work, or machine learning based machine translation? There is no dictionary. We don't have to translate word to word. There is no grammar, no meaning, no context. We are given just pairs of text, and then we perform statistical computation that finds patterns. So if a word occurs in 100 sentences in the first language, if another word occurs in anytime that word occurs in the first language, in the second, another word occurs every time, we could say the first word translates to the second word. And we have to, so one can come up with many statistical rules, hundreds possibly, pretty complex rules. So statistical machine translation was very complicated. There were very complex rules, statistical rules saying, what can we do to say this word in one language translates to the other word? Or sometimes what happens is there's something called fertility. One word in one language translates to 3 words all the time in the other language. Or sometimes nothing in the first language translates to, or a whole bunch of words in the first language do not translate to anything in the second language. And then there is the issue of alignment. Sometimes the subject occurs first, in some other language, the subject occurs, verb occurs second, in some other language, the verb occurs at the very end. So there are lots of rules. For 30 or 40 years, people were looking at developing rules to see how patterns in one language translate to patterns in the other language. So that was statistical machine translation. So what I'm going to do now is we're going to neural machine translation, which is similar to statistical machine translation, but it's going to be based on a new paradigm of computing, not a new paradigm, but a way of learning by machines called artificial neural networks. And I'm not going to go into details of artificial neural networks because that's going to be another few hours if I just wanted to go into that. Okay, so let's look at a paper called Neural Machine Translation. So statistical machine translation was the predominant mode for performing translation in machines till 2016 or so. So Google Translate have been in existence from something like 2007 for the first 8 or 9 years with using statistical machine translation, which was dependent on finding patterns between sentences in language 1 and sentences in language 2, and approaches were very complicated. But let's look at a paper from 2014. It's the first time one can see a published paper that actually gives us good results in using what are called neural networks for translation purposes. And this came from Google. Okay. So this approach is called an encoder-decoder approach. So encoder is a program of some kind based on so-called neural networks. The decoder is also a program. The encoder takes a sequence of words, 1, 2, 3 words in one language, Je suis étudiant, and performs some computation with these three words and produces here some kind of understanding of these three words. Essentially is, if we look at us as human beings, when I hear a sentence, moi eta, moi edon satra. That's the sentence in Assamese. I understand moi, understand edon, understand satra, and then put the meanings of all of them together and form an understanding of the entire sentence in my head. And that's the understanding of the entire sentence. That's called the encoding of the sentence. Then I take that understanding in the head of the entire sentence and decode it. That means produce words in the second language. Moi, edon, satra. I hear the word moi. I hear the word edon, form some understanding together. Hear the word satra. I understand all of them together, one by one. I'm going through some looping process, iterative process, and forming an understanding. I understand the entire sentence. That's called the encoding of the sentence, meaning at some level. Then I start decoding it. Then I start producing it in the other language. I am a student. I produce the first word in the second language, the second word, the third word, the fourth word, and at some point I'll say I'm done translating. So the approach taken is called, it's a paper like I showed from 2014, and this is only 8-9 years ago. They took the encoder-decoder approach. And these are so-called neural network-based programs, but they could be based on some other technology as well. So neural networks are a way of performing computation where we have simple computing units that are connected in some ways. We have one layer of units. We could have other layers. These units are connected layer by layer. The simplest way of building neural networks is called feed-forward neural networks. So we have one layer of units and another layer. From the first layer, every unit in the first layer is connected to every unit in the second layer, and so on and so forth. It always moves forward. That's called the feed-forward neural network, and these have existed for the past 60, 70 years. Okay, people had started working with neural networks in the 1940s, 50s. And these are from, I would say, 1970s, 1980s. At some point, people felt that what should happen is it's possible that we take the output of one unit and fit it to itself. Take the output of one unit and fit it to itself. And it's still a kind of feed-forward neural network, but there are some layers here and there where there is feedback to the unit. So these are called recurrent neural networks. Anytime the output is taken and fed back. So this is a recurrent neural network, a simple processing unit. Suppose it performs some addition, multiplication, that kind of operation, but the results are output at the same time. They're fed back to the neural unit, so it can perform computation, the next input, and some understanding of the previous input. So if this is the iterative version of it, recurrent version of it, but if we want to see what it actually means, it gets one input, it does some processing, produces an output, but the same output is taken into account in the second time cycle. The next input comes in, it takes the second input and some understanding of the first input and produces an output. Now this output here has some understanding of the first input as well as the second input. That's taken into account when the third input comes in to produce an output in the third time cycle. So this is called unrolling an RNN. Sutskever's paper simply uses an encoder. So this portion is the encoder. This portion is the decoder, where the encoder is a iterative processor called recurrent neural network. The decoder is also a recurrent neural network and iterative processor. It takes the first input, for example, the first word, forms a little understanding of it. Then it takes the second word, combines the input word with understanding of the first word, produces an output, takes the third word directly, and a little understanding of the first word and the second word. That's what it is here. It then forms an understanding of the three words ABC. Then something called end of sentence comes in. So W is an understanding of the entire sequence of words ABC, which you can think of as a sentence. So this is the unrolled RNN. And at this point, we have an understanding of the first sentence. That's W. It's the same. It shows a W here. But once it has an understanding of the entire sentence, Moi Adon Satra, it starts producing I am a student, and so on and so forth. The first four cells constitute the encoder. This is the encoder. The rest, the decoder. Both are recurrent neural networks. And here, both have been unrolled. All right, so this paper that I talked about from Suchkever was able to translate from French, from English to French. Okay, so it was able to translate complex sentences. It's the first time people showed that a neural network-based architecture in the form of an encoder followed by a decoder can actually perform good translations. And then if you look at the performance of this paper, what it does is, as you can see, the state of the art, this is 2014. There is some way of measuring how good the translation is. This paper, and I'm not sure what the paper is, it had a score of 37, but Suchkever's paper had a score of 36.5, so it was actually fairly comparable. This paper here, state of the art, it was based on statistical machine translation, a very complex way of performing translation, whereas this was straightforward using neural networks, an encoder followed by a decoder, both encoder and decoder being recurrent neural networks, and then trained on a lot of text of translation, bilingual text of translating from English to French, and it performed fairly well. But let's see, what we have here is a way of measuring how good a machine translator is. And there is something called a blue score, and let's see what this score is. Machine translation performance is measured in terms of what's called the blue score in general. So let's look and see what the blue score is. The blue score is given a reference translation, so we'll have pairs of sentences in one language translated to the other language, and the machine performs translation. Suppose that's a Chinese sentence, and someone who knows Chinese and English well, they translated the Chinese to English, and this is called a reference translation. This is the gold standard. This is a good translation. Now we have a program that possibly can translate this sentence to English in many different ways. One translation, potential translation, the gunman was police kill, wounded police off, the gunman was shot dead by the police, the gunman arrested by police kill. So the machine is trying to perform translation and makes a lot of translations and now wants to see which one is the best translation. Given the sentence in English, it's reference translation, we have a bunch of candidate translations, and we want to know which one is the best one. So what we can simply start doing is we can start looking to see, compare the reference translation with the candidate translations. Just simple comparison. So the reference translation has the sequence the gunman was. In this candidate translation, we have the gunman was. So we have 1, 2, 3 words here in the reference translation and 3 words common. Then we look at the candidate translation number 2, wounded police JF. There is no word in the reference translation in candidate translation. So let's look at candidate translation 3. The gunman was shot dead by the police. The gunman was shot 1, 2, 3, 4. 1, 2, 3, 4. 4 words are common. And by the police, we have 3 other words are common. So we start just looking to see how many words are common between the reference translation and one of the candidate translation. Then we start looking, what's the longest sequence in the reference translation that's present in the candidate translation. So green means 4-gram match. 4 words here are they're directly green or for anyway. So we start looking. So given the reference translation, let's start comparing how many words and how many sequences of words of what length are common, and we come up with a formula. And that's blue, the blue translation. So when we talk about the blue translation score, it just compares to see how many words are common between a reference translation and the translation produced. Single words, 2-word sequences, 3-word sequences, 4-word sequences, and so on and so forth. And then it comes up with some numerical formula combining all of them. Okay. Traditionally, machine translation evaluation is difficult. So what happens is to do a translation well, or to learn translation well, it's great if we can get a sentence in one language and maybe have 3, 4, 5 people translate it to the second language and then perform computation like the blue score computation. Okay, so such covers was the first paper that showed neural network-based translation is possible. Using the encoder decoder architecture. The encoder is a so-called recurrent neural networks, a simple computing unit that performs recurrent iterative computation. The decoder also performs iterative computation. And so that was the first paper. The second paper came out, one of the most influential papers came out in 2015 by 2 individuals named Badano and or 3 people, Cho and Bengio, and they're university people. And let's look and see what they did. Okay. So what we have here, again, it may be difficult to understand what's going on, but let's go and look at the first architecture. So here from the subscriber's paper, that's the encoder and that's the decoder. The encoder takes one input, produces an encoding or understanding of it. It takes the second input, produces an understanding that combines the first 2 inputs. Then that's used with the third input to produce an understanding of then 3 words together and so on and so forth. So understanding of the first word, understanding of the second word, understanding of the third word, understanding of the fourth word happens, and then translation starts happening. Output starts being produced. So one has to wait till the entire sentence has been understood. So as I said, instead of ABC, if I say moi as on satra, I have to understand the word moi as on, satra, then Dari and US will be Dari in Assamese. And then I have an understanding of the entire sentence. Then I start producing I am a student, period will be the US end of sentence in English. And so the point here is that we have to wait till we have processed the entire first sentence to get a full understanding of the entire sentence and start producing in the second language. So what could happen though, sometimes sentences are long. So if we look at a sentence like this, let's see, note that the STM reads, if you look at this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So maybe there are 22, 23 words in this sentence. And when I have to translate a really complex sentence in one language to another language, so if it has 20 words, 30 words, 40 words, if I have to wait till the very end to form an understanding of the sentence and start translating, it's quite possible I could forget what was there in the beginning of the sentence, what was there in the middle of the sentence, and I may just remember what is towards the end of the sentence or some important parts, but I forget most of the sentence before I start translating. So it's simply then what's going to happen here now is that the next paper, Bahdano is going to say, as we understand words one by one, we should make some notations, maybe write something down on a piece of paper saying, I have heard 2 words and this is the most important concept so far. 3 words, the most important concept so far. And that is what is going to happen in the next paper. So this is an RNN unit. This is another RNN, this is an RNN, not unit. This is an RNN processor. There are 2 processors, but essentially it's looking at one word, the first word, looking at the second word, the third word, and last word. When it understands the word X1, moi, as on satra, aru, mur, ghar, nalbarit, it goes on and on and on and on. Suppose I have 50 words. As it's understanding the first word, it is going to produce an output. That output is going to be remembered. So it's going to note something down on saying, this is what I understand so far. At this 81, 82 is some kind of notation, annotation based on the sentence is being spoken, moi, mor, ghar, nagat, jot, kolong namare kanodiase. It goes on and on, a very complex sentence, but often I'm making notes before. And then when I start translating, I look at those notes I wrote when I heard the first sentence, and that is what's called attention mechanism, saying do not wait till you have looked at the entire sentence in the first language. As you hear words in the first language, one by one, yes, form an understanding of the sentence, but make some notation saying what you have understood so far. And when you translate to the second language, use those notations. And that's called attention mechanism. And that attention mechanism actually helped improve translation quite a bit. So here it's from Bahdano's paper. The picture is from someone else. The agreement on the European Economic Area was signed in August 1992, period, that's end of sentence. What happens is European Economic Area, it looks like it remembers or it tries, when it's translating Zone Economic European, it knows what part of the first sentence to focus on. As it's keeping notes, it's able to actually, when it's performing translation, you can go back and look at the notes, look at the annotations, look at what it's stored to figure out how translation should happen better. I think there's another drawing here. It shows the same. It's saying it has the sentence in English, a sentence in French, then most words, the, le, agreement, accord, on, sur. Most words are translated directly, but there are places like this, where European Economic Area, when you translate this, it remembers to go and look at those and perform some computation that moves them around. So it knows when it's translating from one language to the other, as it's translating, it knows what part of the first sentence it should focus on. And this is called the attention mechanism, and that was one of the biggest innovations in 2016 by Bahdano. So machine translation improved a lot. It looks like it's very simple. As we're translating, as we're understanding the first sentence, which could be a fairly long sentence, Do not wait till you have understood the entire sentence to start translating. As you understand the words in the first language, keep some annotations and use those annotations later as you translate into the second language. And that seems like something simple, something common sense, but people didn't know how to do that. Then came Google Machine Translation the paper in 2016. And this is the first time, or this is the time when Google moved from so-called statistical machine translation to neural machine translation. And this paper from October 2016, it says, yeah, we're moving from statistics-based machine translation to the approach taken by Jugal and Badanow, where we have an encoder of an RNN-based encoder for the input. And then we have an RNN-based decoder for the output. And as it produces the output, it's going to be able to look back at what portions of the input could be actually relevant based on annotations. So Google's neural machine translation, and this is from 2016. Let's look. So this is actually, again, I'm not going to go into details here, but this is the same architecture. It's Google Neural Machine Translation System. It's quite similar. It's quite similar to Badanow and Jugal's approach, except that the computing infrastructure used is much more expensive. Badanow and Cho and Bengio, they're from universities. Universities don't have too many resources, but we come up with the ideas, then big companies can go and implement those ideas by spending millions and millions and millions of dollars buying thousands and thousands of GPU machines or hundreds of thousands of GPU machines, and they can make the services available. And so Google's neural machine translation, so look at the number of people, quite likely 1, 2, 3, 4, 5 people. And here it looks like there are 30, 40 people, quite likely a whole bunch of have PhDs, quite likely to spend $100 million or $200 million and made Badanow's approach available to the entire world. Okay, and so the approach is not very different, except that, for example, they used 8 encoder layers of RNN instead of 4 in Badanow. And so it's the same approach, encoder-decoder approach, using RNNs, a special kind of RNNs called LSTMs. It's not important what LSTMs are, but they're recurrent iterative computational units. And Google switched from statistical machine translation to neural network-based machine translation in 2018 or 2016. Okay, so then there is, again, this is a paper from 2019. This is also from Google. Now, Google initially had, I think, in 2007, it had 5 or 6 languages. By 2016, or by 2017, 2018, it had 70 languages. By 2019, it goes to 100 languages. So let's see what happens in this paper. And this is when Google Translation is starting to become big. It said, we introduce our efforts towards building a universal neural machine translation system capable of translating between any language pair. We said, okay, so they're going to now in 2019, they're telling us in this paper how they scale up to 103 languages. Okay, and so let's look briefly. Google's 2019 improvements. Google built a neural machine translation system that can translate from 103 languages to 103 languages. All languages are trained in parallel. So that means it's a huge, huge neural machine translation system. Where given one input in one language, it trains on these 103 pairs of languages at the same time. Okay, and the encoder network is now based on something called a transformer. That's again another complex neural network approach. that uses what's called the transformer, the attention mechanism, saying essentially as you perform computation, remember something of what you have done so far and use it later as you translate. Now, this is an enormous neural network with 120 layers of transformer. So what it does is it has an encoder network, a decoder network. The encoder network forms an understanding of the input, but remembers some annotations from intermediate steps. The decoder network produces the output by looking at the entire meaning of the input, but also looking at notes the encoder took in intermediate steps. And in Sutskever's and in Bahdanav's and the 2016 paper by Google, the encoder and decoder, they were both so-called recurrent neural networks. In 2019, Google changes the encoder network to what's called a transformer-based network, but decoder network is still RNN-based. Okay, and it learns to translate not from one language to another at one language to another, but it learns to translate at the same time. Sometimes we have a lot of data from language 1 to language 2. From English to French, we have 30 million pairs of sentences. From English to Assamese, we may have only 1,000 or 2,000 sentences that have been translated. So what happens is it tries to leverage the commonalities across all languages in the encoder and the decoder. Okay, so this is from the 2019 paper. What we see that when it's learned to translate from one language to another, if it looks at, for example, Indo-Aryan languages, that's Hindi, Bengali, Gujarati, Marathi, these are Dravidian languages, Telugu, Tamil, and so on and so forth. What's going on here is they're saying that if for some languages there is not a lot of data, bilingual data, translating from one to the other, it may be possible to use similar languages that have a lot of data, for example, from Hindi to English, because Government of India publishes documents in both Hindi and English at the same time. Or Bangladesh, for example, BN, publishes Bengali is the official language. They publish their documents in Bengali and English at the same time. So it's possible that for a language like Assamese, for which there is not a whole lot of data, we can use some of the understanding that we have by translating from Hindi to English or Bengali to English and use it for translating from Assamese to English or Assamese to French or Assamese to whatever. So the team compares, this is the 2019 paper, the team compared the representations of multilingual models across different languages. They found that multilingual models learn shared representations. So the representations for languages from one class, one family, they're quite similar. So these are Indo-Aryan languages, they're Turkic languages, Slavic languages, Germanic languages, like here, you'll find Deutsch. Then quite likely Swedish, French, and these are Celtic languages, like there will be Irish, Gaelic, that's Gaelic, then if you look at the African languages, this somehow the representation, internal representations formed for sentences, they seem to cluster together, and this is what's going to be used in dealing with translation for less resource languages. So Google's 2020 editions, Google added 24 new languages in 2022 by leveraging this idea, saying languages that belong to one group or one class, they seem to form in the encoder space, they seem to form representations that are quite similar. So it's added here, as you can see, it added Assamese in 2022. It's May 11, 2022. And it's the first, for Assamese, they were having difficulty finding sentences or in general to be able to translate well from one language to another, say the English to Assamese or Assamese to English, they need 5, 6, 10 million pairs of sentences. So quite likely some government is not doing a good job putting out its documents on the web in both Assamese and English at the same time. So if some government was producing documents in Assamese and producing their exact translation and putting them out on the web, Google would have found all of that, but that was not happening. So for a language like Assamese, they were able to find only about 100,000 sentences. And so in Google 2022, Google did some, if you look at this portion here, Google says in their blog, 2022 edition was a milestone for Google Translate. It added Assamese and 23 other languages by using what's called the zero-shot machine translation approach when a machine learning model sees monolingual text. So what happened in the case of Assamese, they were not able to find any good a set of sentences that have been translated from English to Assamese well. So they found 100,000 sentences in Assamese on the web, and they did some processing to know that they're good quality sentences. And then what they did was they used what's called the masked language modeling. So what they would do, they learned to translate from Assamese to Assamese, but they'll take an Assamese sentence, they'll blank out or mask out, cover some words in Assamese and learn to translate it into good Assamese. So it's saying it masked some words on one side. So this covered it up. So moi as on satra, maybe it'll cover up as on moi blank satra, and it'll try to translate to moi as on satra. So that's what masked language modeling is. It learns to translate garbled Assamese where some words have been covered up to translate to fluent Assamese. It did it for all of these languages because they didn't have bilingual corpora, and was able to add Assamese and Bhojpuri and Dogri, and I think Maithili and Sanskrit and others. And right now, Google is working on 1,000 languages of the world, and they want to put the next project they have in mind is to put 1,000 languages to translate from one language to the other language. All right, so I think that's my entire presentation. So this has taken us from a statistical machine, or classical machine translation that people used in the 1970s, 1980s, 1960s, to statistical machine translation used from 1980s to 2016 or so, then neural machine translation from 2016 to now. And I looked at only one task. There are many, many tasks one can perform in natural language. One is translation, the other is question answering, other is writing essays, another could be developing a search engine properly, another could be summarization. There are tens of tasks one can perform, but I wanted us to go through one task that everyone seems to know about now, translation, machine translation, and see where it started, how it progressed from one time point to another time point, and the rapid progress that had been made from 2016 on to now. So Google had been able to use 130 languages. So let's do one thing now. Let's see. So if anyone has any questions now, I can answer. My presentation is finished. It's 9 o'clock. I wanted to do it in an hour, but I'm open to any kind of questions people may have.
Thank you, Professor Kalita. And that was really an insightful talk, and we learned a lot. So before we go to the Q&A, Professor Hiroina Nath, who is a member of 15-minute Hikka, has an announcement, quick announcement to make.
ধন্যবাদ আমি আজি আসলতে বহুত কথাই শিকিলো আমি যে সকলোৱে ছাত্ৰ ছাত্ৰীসকলক উদ্দেশ্য কৰি কৈছো যে হাতে হাতে লৈ ফুৰা মোবাইল ফোনটোৱে যে ইংৰাজীৰ পৰা অসমীয়ালৈ অনুবাদ কৰিব পাৰে বা অসমীয়াৰ পৰা ইংৰাজীলৈ অনুবাদ কৰিব পাৰে তাৰ আৰৰ যিবিলাক কথা কাৰিকৰী কথা বা ঐতিহাসিকভাৱে যি ধৰণে এই প্ৰযুক্তিটোৰ বিকাশ হৈছে সেই সম্বন্ধে অধ্যাপক যুগল কলিতা দেৱে ইমান সুন্দৰকৈ 1.5 ঘণ্টা ধৰি তেখেতে আমাক কথাখিনি কৈ দিলে আৰু তাৰ কাৰণে 15 মিনিট শিক্ষাৰ তৰফৰ পৰা আমি তেখেতক আন্তৰিক ধন্যবাদ জ্ঞাপন কৰিছো মই কম্পিউটাৰ বিজ্ঞানৰ ছাত্ৰ নহয় বা মই কৃত্ৰিম বুদ্ধিমত্তাৰ ছাত্ৰও নহয় মই অৰ্থনীতিৰ ছাত্ৰ তথাপিও এই কথাখিনি তেওঁ ইমান সহজ সৰলকে বুজাই দিছে যে মই বুজি পাইছো গতিকে মই আশা কৰিছো যে আমাৰ এই অনুষ্ঠানত উপস্থিত থকা ছাত্ৰ ছাত্ৰীসকলেও এই কথাখিনি কাৰিকৰী কথাখিনি সম্পূৰ্ণৰূপে নহলেও আনখিনি কথা ভালকে বুজি পাইছে আৰু এটা কথা নিশ্চয় উপলব্ধি কৰিছে যে তেওঁলোকে কম্পিউটাৰ বিজ্ঞানেই যে পঢ়িব লাগিব তেনেকুৱা কথা নহয় ভাষা তত্ত্ব বা সাহিত্য পঢ়িও বা পৰিসংখ্যা বিজ্ঞান পঢ়িও যে এই যেটো প্ৰসেস নেচাৰাল ল্যাঙ্গুৱেজ প্ৰসেস বা কৃত্ৰিম বুদ্ধিমত্তা বিকাশৰ যেটো প্ৰক্ৰিয়া সেই প্ৰক্ৰিয়াটোলৈ তেওঁলোকে বৰঙনি যোগাব পাৰে সেই কথাটো এই যেটো আজিৰ বক্তৃতাটোৰ জৰিয়তে ওলাই পৰিছে বুলি মই ভাবিছো আৰু ছাত্ৰ ছাত্ৰীসকলে যদি হেতু উপলব্ধি কৰে তেতিয়া হলে আমি ভাবো যে আমাৰ যেটো এই প্ৰয়াসটো সফল হ'ব আমাৰ পিছৰ যেটো অনুষ্ঠান 2 সপ্তাহ পিছত যেটো আমাৰ অনুষ্ঠান আমি অনুষ্ঠিত কৰিম হেতু আসলতে আমাৰ এই 15 মিনিট শিক্ষাৰ 2 বছৰ সম্পূৰ্ণ হোৱা উপলক্ষে অনুষ্ঠিত কৰা এটা বক্তৃতা এটো এটা বিশেষ বক্তৃতা আৰু এই বিশেষ বক্তৃতাটো প্ৰদান কৰিব অসম বৈভৱ কৰ্কট ৰোগৰ বিশেষজ্ঞ চিকিৎসক তপন কুমাৰ শইকীয়াৰ এটা বক্তৃতা আমি আশা কৰিছো যে ছাত্ৰ ছাত্ৰীসকলে এই বক্তৃতাটোত উপস্থিত থাকি আমাক উৎসাহিত কৰিব তথা আমাৰ এইটো প্ৰয়াসক সফল কৰিব ডক্টৰ শইকীয়াই কৰ্কট ৰোগৰ বিষয়ে কিছু সজাগতামূলক কথা আৰু আমাৰ ছাত্ৰ ছাত্ৰীসকলে যিয়ে অধ্যয়ন নকৰক কিয় তেওঁলোকে কি ধৰণে কৰ্কট ৰোগৰ সম্পৰ্কে সজাগ হৈ আমাৰ সমাজত কৰ্কট ৰোগ প্ৰতিৰোধ কৰাৰ ক্ষেত্ৰত বৰঙনি যোগাব পাৰে সেই সম্বন্ধে তেখেতে এই বক্তৃতাটোত উল্লেখ কৰিব গতিকে মই ছাত্ৰ ছাত্ৰীসকল আৰু ইয়াত উপস্থিত থকা আন সকলোকে আহ্বান জনাও তেওঁলোকে যাতে এই বক্তৃতাটোত উপস্থিত থাকে হেতু হ'ব ফেব্ৰুৱাৰী মাহৰ 19 তাৰিখ দেওবাৰে 8 বজাত সন্ধিয়া 8 বজাত তাৰ লগতে আজিৰ আমাৰ যেটো অনুষ্ঠান তাত আমাৰ সহযোগী মহাবিদ্যালয় কেইখনমান আছে বিশেষকৈ আজি দুধনৈ মহাবিদ্যালয়ৰ বহু ছাত্ৰ ছাত্ৰী আমাৰ অনুষ্ঠানটোত উপস্থিত আছে তেওঁলোকলৈ আন্তৰিক ধন্যবাদ জ্ঞাপন কৰিছো লগতে আমাক তেওঁলোকৰ হৈতে যোগাযোগ কৰাই দিয়াৰ কাৰণে বিশেষকৈ ডক্টৰ দীপাঞ্জলি দেৱী আৰু ডক্টৰ বন্দিতা বৰবৰালৈ আন্তৰিক কৃতজ্ঞতা জ্ঞাপন কৰিছো দুধনৈ কলেজৰ লগতে আন কেইখনমান মহাবিদ্যালয় আজি অনুষ্ঠানটোৰ সহযোগী হিচাপে আছে তেওঁলোক এই কলেজ মহাবিদ্যালয় কেইখন হল গুৱাহাটীৰ এছবি দেওৰা মহাবিদ্যালয় ক্ষেত্ৰীৰ ডিমৰীয়া মহাবিদ্যালয় জাগিৰোড মহাবিদ্যালয় পুৰণিগুদামৰ ডক্টৰ বিনসি কুমাৰ বৰুৱা মহাবিদ্যালয় আৰু নগাঁও কন্যা মহাবিদ্যালয় আৰু এই অনুষ্ঠান কেইটাক আমাৰ লগত সংযোজিত কৰাৰ কাৰণে ডক্টৰ ধৰ্মেন্দ্ৰ নাথ ডক্টৰ বিপুল কুমাৰ দাস ডক্টৰ ভৱেন চন্দ্ৰ নেওগ ডক্টৰ পুণ্যলতা বৰগোহাঁই ডক্টৰ অবিনাশ ভৰালী আৰু ডক্টৰ কুলেন দাসলৈ আমাৰ মঞ্চৰ তৰফৰ পৰা 15 মিনিট শিক্ষাৰ তৰফৰ পৰা আন্তৰিক ধন্যবাদ জ্ঞাপন কৰিছো পুনৰবাৰ আজিৰ অনুষ্ঠানটোত উপস্থিত থকা আটাইলৈকে ধন্যবাদ জ্ঞাপন কৰিছো আৰু তাতোকৈ আমি আজি অতি সৌভাগ্যৱান যে অধ্যাপক যুগল কলিতা দেৱে আমাক 1.5 ঘণ্টা সময় দি আমাক এই নেচাৰেল ল্যাঙ্গুৱেজ প্ৰসেসিংৰ বিষয়ে বুজালে জনালে আৰু তাৰ বাবে তেখেতক পুনৰবাৰ আমাৰ টিম 15 মিনিট শিক্ষাৰ তৰফৰ পৰা ধন্যবাদ জ্ঞাপন কৰিছো হিৰক তোমালৈ আগবঢ়াই দিছো
ধন্যবাদ স্যার আমাৰ আৰু questions আছে from the chat on Zoom. So Jubin asked for decoding to occur, coding is necessary, but what is the conceptual relationship between coding, decoding, and translation?
Encoding, অন্যবিলাক বাদ দিওঁ ধৰা মই বা তুমি এটা অসমীয়া বাক্য ইংৰাজীলৈ অনুবাদ কৰিব বিচাৰিছো আমাৰ এজন বিখ্যাত মানুহে কিবা কথা কৈ গৈছে ৰাষ্ট্ৰপতিয়ে কিবা এটা কথা কৈ গৈছে বা অসমৰ মুখ্যমন্ত্ৰী এতিয়া কথা কৈ গৈছে অসমীয়াত আৰু কোনোবা এজনে এইটো অনুবাদ কৰি গৈছে এনেকুৱা হ'ব পাৰে যে আমি ৰম মুখ্যমন্ত্ৰীয়ে এটা সম্পূৰ্ণ বাক্য কৈ দিলে তেওঁ টান শব্দ ব্যৱহাৰ কৰে অসমীয়াত ক'লে তেওঁ দীঘল দীঘল বাক্য কয় এটা বাক্যত 50টা শব্দ থাকিব পাৰে এই এনকোডিং মানে হ'ব আমাৰ মগজত বা কম্পিউটাৰৰ মগজত কম্পিউটাৰত এই এটা শব্দ শুনি গৈছে শুনি যোৱাৰ পিছত আমি কি ধৰণে মানে মনত ৰাখিছো তেওঁ কি ক'লে এতিয়ালৈকে দুটা শব্দ ক'লে তিনিটা শব্দ ক'লে সেই তিনিটা শব্দৰ মাজত সম্বন্ধ কি শেষত আমি আটাইখিনি শব্দ শুনাৰ পিছত তেতিয়া যিটো বস্তুটো আমি বুজি পালো সেইটোৱে এনকোডিং আৰু গতিকে এনকোডিং আমাৰ ভালদৰে হ'ব লাগিব তেতিয়াহে আমি বুজি পাব লাগিব বস্তুটো তেওঁ কি ক'লে আমি যদি অনুবাদ কৰিবলৈ আৰম্ভ কৰো ইংলিছলৈ অনুবাদ কৰো হিন্দীলৈ অনুবাদ কৰো বেংগলীলৈ অনুবাদ কৰো আমাৰ মুখ্যমন্ত্ৰীয়ে যি কৈ গৈছে এনকোডিংটো সেইটোৱে বুজি পোৱাটো আৰু ডিকোডিংটো হ'ল এইটো আমাৰ বুজি পোৱাৰ ওপৰত নিৰ্ভৰ কৰি ইটো ভাষালৈ অনুবাদটো কৰা আৰু translation is very dependent on the encoding process. Encoding process we need to understand the various components of the input sentence. How each word relates to other words in the input sentence. And because the first sentence could become very long, quite often we have to somehow maybe if it's someone is doing this some people are very good translators, but quite likely if you don't do it well, we have to make some notes in between. We hear the first two words and make a note. The second, another word, make a note. And when we're translating, that means decoding, we'll go back and look at the entire understanding of the first sentence as well as the intermediate notes we took. So encoding, decoding, translation, they're all connected.
Thank you. I hope it answered Zubin's question. So another question from Zoom chat. For translation to be perfect, we also need standardization like Unicode. Can you discuss?
Unicode is simply a way of, so there are, let's see, hundreds of writing schemes. So in English, we have the letters A, B, C, D, uppercase, lowercase. In Assamese, we have O, Ka, Akar, Digurikar, Husarikar, all of that. So each one has to have some kind of an ID on the computer. So, and Unicode is simply giving an ID to each character we want to produce on a computer. So Unicode is necessary for representing the letters in a language. And it's just a representation of ID, saying letter number 1 is A, letter number 2 is B, letter number 2000 is O, letter number 2001 is A. So they're in the process of translation. Unicode is just a way of saying which character has to come out. That's it. There is nothing more to it. Unicode is simply a numbering scheme for characters and what they look like on the computer screen.
Okay, RT did not write properly, so she is clearing that that was not her question. So she wants to talk. So,
Hirok, there is another question above. That's from Roland. So maybe can you read it as well?
I think we're also running out of time, so we have to, I guess, limit our discussion to some extent. And you can also write to Professor Kalita to his email. So Roland asked, had some brief experience programming a basic LSTM on a small number of tokens 4 years ago as a programming exercise, and just basically wondering what the high-level difference or evolution is with GPT-3 compared to a simple LSTM RNN.
LSTM-based RNN. LSTM is a recurrent neural network unit. So there is the very simple recurrent neural network units. Those are called RNNs. LSTMs are a little bit more complicated. They have, they can remember things a little longer. They have 3 kinds of gates: input gate, forget gate, and output gate, but that's not important. LSTMs are kind of RNNs, whereas GPT-3 or GPT these days, they use what's called a transformer. A transformer is something somewhat like a CNN. It doesn't do recurrent processing. So transformers came out in late 2017, the idea of a transformer. And so let me try to explain this. Suppose I want to I want to understand one sentence well. Moi Ramor Ghorle Jam Kianu Tar Ghor to Guahatit. Or More Ghor Nogar Gaut. Moi Ramor Ghorle Jam Kianu Tar Ghor Guahatit. Or More Ghor Nogout. Or Muradi Guahatit Kamafe. Moi Ramor Ghorle Jam Kianu Tar. I want to go to Ram's house because his house is in Guwahati. His tar. He শব্দটো বুজি পাবৰ কাৰণে tar শব্দটো মই ৰামৰ ঘৰলৈ যাম কিয়নো তাৰ ঘৰটো tar মানে কাৰ মোৰ নে ৰামৰ এইটো বুজি পাবৰ কাৰণে we have to understand relationship আমি শব্দবিলাকৰ মাজত সম্বন্ধ বুজি পাব লাগিব সেইটোকে কৰিব পাৰে এই attention mechanism যেটো কলো এইটোৱে ভালকে কৰিব পাৰে শব্দবিলাকৰ মাজত এটা বাক্যৰ ভিতৰত বিভিন্ন শব্দ আছে সিহঁতৰ মাজত সম্বন্ধটো কি সেইটো কয় self attention মানে এটা শব্দ শুনি থাকোতে তাক বুজিবলৈ আমি আগৰ শব্দবিলাকলৈ মন পেলাব লাগে এইটো কয় self attention আৰু transformer attention mechanism টো ভালকে implement কৰে গতিকে transformer LSTM নাই GPT-3 transformer আছে LSTM 9 এতিয়া মই তেনেকে কলো Google Translate encoder part 2 transformer based decoder part 2 LSTM based ইহঁতে কলে decoder part 2 transformer দৰকাৰ নাই because RNNs or LSTMs do very well and they're faster, they're more efficient, but the transformer encoder in the transformer in the encoder seems to produce good translations. So GPT-3 uses transformers. It does not use LSTMs. But transformers you can simply download these days code that implements transformer and start using it.
Okay, I hope that answered your question. So I think it's getting late in Assam, and also we are like 1.5 hours past. So thank you again very much to Professor Kalita, and also to all the students and the attendees who asked really questions in this interactive session. With that, we would stop the video recording for today's session, and thank you all.
But